This is Steve from Crondall. Yeah, what you need to know about Steve? So what you need to know about Steve is he's famous for sailing the Atlantic in his time, but that pales into insignificance to the fact that he actually gave me my first ever job in the oil and gas game about 25 years ago. Over to you, Steve.
Thank you, Graham. A subsea tieback consists of four main elements. We have the subsurface part, the drillings and completion. We have the subsea production system, we have the flow lines, and we have the host modifications. And the subsea, the tieback of the future really focuses on the middle two. That's the subsea production system, which Gordon's been talking about, and the subsea flow lines. And my presentation is looking at the subsea flow lines. So the first question is, are subsea flow line costs significant? I guess we all have a feeling that they are. These data is from two recent projects and suggests costs of something like 30 to 45% of the total SURF and SPS EPCI costs. So I think the conclusion from that is that the costs are indeed very significant. And the focus of our study is to look at, can we lower the flowline costs either by looking at new technology or by applying the circular economy, by looking at reuse. I've obviously been working longer than Graham, as he pointed out, and even in the time that I've been in the industry, the fundamentals of flowline technology hasn't changed all that much. What we do is we buy pipe, usually seamless pipe because of the thick wall and the size. We put some quite expensive, though for any coaters here, no doubt good value, insulation on it, and we then install it. And we can install it in a number of ways, but the most common way is to fabricate the pipe in a spool base, install it on an elegant reel barge, trench it for protection, and possibly other things. And at the end of life, we decommission in situ. So we clean the pipe, mattress the ends, and we leave it in situ. There's no reuse taking place. And part of this study is to challenge this and to say, well, can we do that? Can we do that differently? We've looked at two or three things as part of that. We've looked at flow assurance. We've looked at alternative flow line technologies, and we've looked at the circular economy. So the end of the presentation is really the cost differences, but I thought I'd put this in now just to try and maintain interest. We've looked at costs for 6-inch, 8-inch and 10-inch, but this is one slide that just shows one of these cases. And what we've done is we've taken the orange bar in each case is the existing technology. So this is the existing technology. Along the bottom here we've got number of reuses, and then the different coloured bars are some of the different options that we looked at. And the results are pretty dramatic, really, we think. It certainly seems possible to get something like 50% reduction in cost. And that's helped by the technologies, but that's probably dominated by the reuse aspects. So I'm hoping this is going to maintain interest in my presentation. So, three things: flow assurance, technology of flow lines, and reuse. So starting with flow assurance. Currently, there's really two ways of doing it. We can keep the fluids hot, and we do that by applying insulation, or we chemically treat with inhibitors, which clearly require some form of umbilical or service flow line. quite often we will combine the two, so we'll quite often have insulation and chemicals. In some longer systems, we might also include round-trip pigging, but for small pools, we think that's quite unlikely, because it requires, obviously, two flow lines. So in looking at flow assurance, our aim was how could we eliminate insulation and how could we minimize chemical injection? And it seemed to us that there's two possible solutions that might allow that. The first is cold flow, and for anyone who's studied cold flow, quite a lot of cold flow studies have actually taken place, but we're not aware of any systems actually going into operation. What cold flow does is it modifies the fluid behavior by crash cooling the fluid through the point where hydrates or wax may form, and then the slurry, the resultant slurry, is pumped to the host facility. Quite a lot of work's been done by Syntef on this, supported by BP, I believe. We think it's quite an interesting technology for really long distances and significant sizes of pipeline, but we don't think it's of any particular interest to small pools. You need quite a significant amount of facility to make it happen. It's also not got much of a track record. The other option that we are really quite interested in is advanced surface preparation. And by that I'm talking about the internal coating of the pipe. And the thought process goes, why don't we modify the pipeline inside surface so that the hydrates and the wax and whatever else, asphaltenes, don't deposit on the pipe wall and cause a blockage. And the multicoloured picture up there shows a surface coating that we all use, and in lots of industries we use lots of internal surface coating. So the question is, why aren't we using this technology for pipelines? To realise the flow assurance benefits of internal surface coatings, we need two things. We need low surface energy, and this stops the deposits from forming on the wall. And we need low surface roughness, and that reduces the friction on the system and allows everything to flow more easily. Even though advanced coatings are not actually available as yet, the good news is that serious technical companies are doing work on advanced polymer coatings at the moment. And examples of this, Whitford Plastics have a Xylan coating made of PTFE, and Victrex are specialists in formulation of PEEK and are working with Magma on their M-pipe composite pipe. So these are high-tech materials, not to be confused with some of the simpler and less technical, I suppose, polymer coatings. And I think most people in our industry, and I guess I count myself in this, we've spent quite a lot of time understanding steel materials, but of course there's a massive difference between high-tech polymers and typical polymers. In addition, the industry actually does use some internal coatings, and a couple of examples there. There's a tuboscope coating, which is used downhole, with good results. And there's various sorts of flow coating that are put on pipelines. And the purpose of these coatings is to reduce the pressure loss, so reduce the pumping or the compression requirement. But that last case doesn't do anything for the more complicated flow assurance. And also worth mentioning that composite pipe offers similar internal surface to, for example, the Victrex system, and similar benefits. So composite pipe may provide us with an opportunity to try internal coatings without going through the technical work associated with putting it on steel pipes. I think those figures, I think the black one is Victrex PEEK coating, and the graph is just showing different surface energies. So to summarise internal coatings, we think coatings exist which have the potential to eliminate insulation and flow assurance chemicals. They'll also protect the pipe against internal corrosion, and they could also simplify operations. Obviously in systems where the pipe where the fluid needs to be kept hot, in shutdowns, then we have to go through a fairly complex, we have to depressurize or add more chemicals or shut down in a certain way. So having coatings that can really manage the deposition could be a significant step forward. Protecting against corrosion is clearly also important where we have potential for reuse. It's clearly important to be able to hand the pipe over in good condition for the next user. However, there are no field-proven systems at the moment. We have systems downhole, but there are no systems which are proven in a pipeline environment. And generally, work across other industries with coatings don't apply anything like the same pressure which we have in our upstream production systems. So that is certainly an item requiring further work. So we need to do significant application-specific research and testing. We also, if we move on to this technology, which we would only do if we have significant savings, that may imply increased risk of blockages, and we may need to do further work on monitoring and mitigation to manage that risk. I should perhaps say I think the conventional way of managing flow assurance is very effective, and I think in recent years or in the last decade or so we've had very, very few blockages. But that also raises the question, do we perhaps at times over-engineer? And my own experience of an upstream chemical injection system is that we stopped using the system when it broke and flow continued. So I think there is some evidence perhaps to suggest that we can sail closer to the wind with regard to this. A key point is that these coatings are probably not suitable for conventional welded construction, and this may be one of perhaps 2 or 3 key reasons why pipelines haven't used internal coatings for flow assurance in the past. We have to do something at the weld. Which brings me neatly on to perhaps getting rid of the weld. Mechanically connected pipelines are not a new idea. They've been around, connectors have been around for a very long time, and we've looked at these technologies in 2 joint industry projects, and there's a joint industry project up on the blocks at the moment, which DNV are trying to get underway. Every well uses mechanical connections, so mechanical connections in our industry are very well understood and should be very high integrity. But of course, in our industry, we work in silos, and I think pipeline people don't talk to downhole people, so perhaps that's a disadvantage. This slide shows 4 different connection systems, and they goes in the same order as the table. So GMC on the top is a pin and box type connector. Zap lock, which is a friction stab. We have a threaded and coupled connector similar to those used downhole, the Vallorac FAM system, and then Marine Direct's rapid pipe at the bottom. So all these connection systems have potential to be used in pipelines. Possibly work in a slightly different way. Some of the connectors you would weld onto the pipe. So you could imagine having 2 or 3 or 4 or 5 or 6 pipe joints welded together in the spool, and then the connections welded onto the end, and then they're made up offshore. The VAM connection is more obvious to use single pipe joints, so we'd make up 12-meter joints. And there's advantages and disadvantages in each. But in each case, it would appear possible to internally coat the pipeline in those sorts of lengths. And as the note is on the bottom of the table there, all the connectors are really designed on the basis that the strength of the connector and the fatigue life of the connector is better than a welded pipe, so that's a good starting point. So summarising connections, they enable internal coatings. They provide significant advantages for recovery and reuse. The T&C connector enables the use of high-strength steel, which may not be weldable. And the impression we get is that there is an opportunity to reduce capex by using this technology. There's also potentially less man-hours required in constructing a pipeline, so there may be an HSE benefit to be identified. Inevitably, there are disadvantages with anything as well. Otherwise, we'd be using it all the time. There is a reliability concern, whether fair or indeed unfair, that a mechanical connection has a higher probability of leaking than a welded joint, and this can only really be addressed by more work. Some of the designs perhaps have more work to do on long-term integrity management for use in a pipeline, and that might perhaps apply to connections which are designed initially for different applications. The connector to pipe interaction, clearly the connector is a larger piece of material than the pipe, so there's a stress discontinuity between the larger connector and the thinner pipe, and that can cause strain localization into the pipe itself. That would just need work to detail design. And there is a limited track record for flow lines, though of course not for use overall. It's because I didn't have my notes. Only got one slide on composite pipe. It's an interesting alternative to steel pipe, and there are serious products from both airborne and magma. There are flow assurance advantages, a number of them. In particular, the smooth internal surface plays to some of my earlier slides. Corrosion and erosion resistance, particularly suitable for reuse, installation by common vessels, and real advantage in tie-ins. I mean, Gordon mentioned the possibility of using composite pipe for tie-ins. Well, it could be that we just install a flow line, we pull the flow line up a J-tube, we lay the flow line down next to a well, and we just pull that flow line straight into the well, something that you can't do with a steel pipe. But there are some limitations, size currently, limited supply chain and track record for flow lines, even though they're used quite often in other applications. And composite pipe is significantly lighter than steel pipe, which wouldn't be a surprise. So there is work to be done on hydrodynamic stability, and I'll touch on that in my next couple of slides. So having looked at technology, we then looked at reusable pipelines, recognizing that most existing flow lines are decommissioned in situ. And there's three key drivers, we think, for reuse of flow lines. The first is the commercial arrangements, and I won't go into that, but I think having a pipeline which is used by operator 1 twice is clearly easy to do. Having a pipeline which is used by operator 1 and is then used by operator 2 raises a series of questions. We've just looked at this from the perspective that if there is value in this, then the commercial arrangements will come. But there does need to be a lot of work, I think, done on that. We've also assumed the pipe is not returned to shore between deployments. This is a fundamental. A lot of the value in reuse is lost if we bring the pipe to shore and then remobilize it again. So we're looking at bringing the pipe back onto the boat, comprehensive inspection on the boat to assure integrity, and then installation in the same mobilization. And then the last point is the on-bottom design. which Graham introduced. I'll go through these next couple of slides slightly more quickly. On stability, stability on bottom is clearly a factor. The pipe needs to be stable under the tides and wave loading. And the work that we did suggests that in the northern North Sea and in the central North Sea, the pipes are basically stable on the seabed. In the southern North Sea, they're not. So we'll have to do something else for that. Clearly, as we put on more wet insulation, the pipe becomes less stable, but generally that problem can be solved in the northern North Sea and the central North Sea. But the composite pipe is nowhere near stable, and so we need to look at trenching or adding weight or adding mats or some form of anchoring. We also looked at lateral buckling. Conventionally in the North Sea we trench and bury, and the pipe, if it's going to buckle at all, it upheaval buckles. If we lay a pipe on the seabed, it's going to go into a snake when it goes into operation. And we looked at, for typical small pools, temperatures and pressures and pipe sizes, is this going to be a significant issue? Fundamentally, it can be managed. I think most of the cases that we looked at, the pipe can just be laid on the seabed. At slightly higher temperatures and pressures, you may have to do a bit more work to make it acceptable, but basically it will be acceptable. So moving on to the costs. So we've looked at a few technologies. We've thought about reuse. And in our cost assessment, we looked at 3 different sizes, 2 different lengths, carbon steel, CRA or composite pipe, different methods of joining the pipes together, insulation or internal advanced coatings, and we looked at 1, 2 or 3 uses. For the reuse cases, we added additional cost for smart operational monitoring. The aim of this is to understand the corrosion and particularly to understand any deposits that might form. And we added costs for offshore inspection on the boat to make sure that we can be sure of putting down in second and third and ultimately more uses, good condition equipment. And we're not returning the pipe to shore until the final use. Each of our cases accounts for bringing the pipe to shore ultimately. And we looked at typical small pools operating conditions. So I've got 3 slides here looking at the different sizes. And I think the key thing to stress is that in every case we seem to be looking at significant cost savings. Of course, when we go into more expensive pipe, we get more cost savings because the pipe's a bigger percentage of the overall cost. 10-inch doesn't include composite pipe because composite pipe isn't available in this size. Going on to 8-inch, we're seeing the same trends. Composite pipe's the blue here. Composite pipe not so competitive straight away at 8-inch, but becomes more interesting in subsequent uses and certainly when compared with CRA. And looking at 6-inch, again the same trends, the same benefits for mechanically jointed pipe. Composite pipe now looking more competitive across all the cases. And an additional small saving if we go into longer pipelines. So this is my last slide. I think other than a thanks one. Pipeline reuse appears to offer significant savings. It's a significant conclusion, this, because we don't do it, but the numbers really do seem to stack up. Of course, there's things about it that we don't know, but the effect is so significant that we believe that even on that basis, we believe that there will be significant savings. Mechanical connectors show promise, particularly with regard to reuse and their ability to enable more advanced coatings. But more work needs to be done to demonstrate reliability, particularly against leaks. Composite pipe, we also feel is a technology which is going to be used more in the future, and it's particularly competitive in small size. It's ideally suited to reuse, and I think for some tiebacks where you may have 15 million for the pipeline and 15 million for a new riser, the ability to put a composite pipe up a J-tube is of great benefit. However, everything I've talked about really needs some further work, and that includes the commercial models. So Graham put up a note of thanks, but we really did get a lot of help from the companies noted here. I won't mention any one because really everyone was very, very helpful, and we couldn't have particularly put together the costs without them, so thanks very much indeed. Crondall have a stand here. It's in the new floating ideas section, and I'd be delighted to discuss any of this. Thank you for your attention.